Okay, good evening. Am I audible? Okay, fine. Hello, everyone. So, good evening or probably good night. I'm not really sure about this. So, to start with, I just wanted to clarify this thing that whether my screen is visible or not, and the other thing being that whether, okay, good evening, Payal. Good evening, Naresh. Good evening, Priyanka. Can I just know if I'm audible or not and whether my screen is visible or not, the PowerPoint presentation, so that we can get started. Good evening, Neha. So, am I audible? Is my voice clear enough? Okay, fine. So, if audio is okay and my screen is also visible, then probably I can get started. So we actually, in the last class, we discussed almost everything about trees, and we were discussing a few questions on BST, binary search trees, right? And this is what we had to discuss today. So there were a few questions that I just wanted to discuss about. So this is the this particular thing, that how do you construct a unique binary search tree using pre-order traversal and post-order traversal. Fine. And I actually took a very random example. So in this particular class, I'll take a previous year question and try to solve that. So in this particular question, they are saying that we are having a pre-order traversal of a binary search tree. Fine. So this is the pre-order traversal of the binary search tree, and we have to find the post order traversal of that binary search tree. Fine. Then how do we do that? So in order to find out the post order traversal of a tree, we will have to first construct that particular binary search tree. And how do we do that? We have discussed the procedure. So for the very last time, I'll again repeat that. So pre-order traversal is this. Then what would be the in-order traversal for this particular binary search tree? The in-order traversal would be the sorted elements, these particular elements in sorted form. So if I have to sort them, then they would probably look something like this: 2, 6, 7, 8, 9, 10, 15. Okay, so there is 12 as well, 15, 16, 17, 19, 20. Fine. So this is the in-order traversal for the same binary search tree, because binary search trees have a property that there is in-order traversal is always in ascending order, right? So now if we try to construct, so now we are having a pre-order traversal and we are also having an in-order traversal. So now we can very well go ahead and construct our binary search tree, and the procedure for that is same as we do in binary trees, that we process all these elements one by one. Fine. So we first of all will be processing 12. So whenever we process 12, we'll make a root node for that, and we will see that what all elements should come to its left and what all elements should come to its right. Fine. So 12, and then I have 2, 6, 7, 8, 9, 10. And to the right, I should have 15, 16, 17, 19, and 20. Fine. So now what is the next element that I have to process? 8. So I'll process this element and make this as root, and I'll move 2, 6, 7 to its left subtree and 9 and 10 to its right subtree. So that is how I will one by one keep processing each and every element. So now I have to process 6. So how do I process 6? I will move I will make a new node for which will only contain 6, and 2 will move to its left and 7 will move to its right. Fine. And then this particular thing is also processed, 7 is also processed, because they are already single nodes only. And then I need to process 9. So once I process 9, so 9 will become the single node, and 10 will move to its right. 10 will move to its right. Why? Because in the in-order traversal, 10 was after 9, right? And as you can see that this is also following the binary search tree property, that all the elements to the left, or all the elements in the left subtree should contain the elements less than this particular element. So this particular property should be valid for each and every node. So now we will actually process 10 is already processed because it is already like a single node only. So now I need to process 16. Fine. So once I process 16, I will make 16 as the only single element node, and I will move 15 to its left and 17, 19 and 20 to its right. Fine. And now I need to process 15. So 15 is already processed because it is only a single node, a single element node. So I need to process 19 now. So how do I process 19? I make 19 as the only node, and then I move 17 to its left and 20 to its right. So I hope you were able to get that as to why did I move 17 to its left and 20 to its right, because in my in order traversal 17 is to the left of 19 and 20 is to the right of 19. Fine. So this is how I was able to construct my binary search tree using only pre-order traversal. Fine. Because once I have my pre-order traversal for the binary search tree, I can by default get my in order. So after constructing the tree, I need to give its post order traversal. How do I give its post order traversal? Post order traversal is LRN, and we have actually discussed this thing in the last class also, that how do we find out the post order traversal of a binary search tree. So I am actually going to go forward in a little quicker way, and I'll find out the post order for this particular tree. So if we go ahead, then we have to first go to the left, then again left, and again left. So now we go to the left, there is no other element to the left and there is no other element to the right, so we process this particular node. So 2, and then 7 will be processed, then 6 will be processed, then 10 will be processed, then 9 will be processed, then 8 will be processed. So I'm like going in a very fast way, but probably you can you'll be able to get this as to what is the how to find out the post order traversal. Fine. So this is the answer that this is the answer, right? Option B. So this is how we first, given a pre-order traversal, we first construct its BST, and then we because in the question they were asking that we have to find out the post order traversal of the tree, so that is why we constructed the tree and we found out the post order. So this was the last thing that we were discussing about binary search trees, and there is one more thing which is important in binary search trees, and that is that how do you do deletion in binary search trees, because actually the insertion in binary search tree is relatively easy. How do you do insertion in binary search tree? So let's say I have to add 12, 9, then 13, then 11, then let's say 2. So these are the 5 nodes that I have to insert in my binary search tree. Then how do I insert? First of all, 12 will be inserted. Now I have to, so wherever I'll find out the empty space, I'll insert that. So 9 has to be inserted, and 9 is less than 12. So I came over to its left, and over to its left there was no node, so I actually inserted 9 in here, right? So now I have to do the insertion for 13. So how do I do the insertion for 13? So I compare 13 with this particular node. Now because 13 is actually greater than 12, so we go to its right. So after going to its right subtree, there is actually no node to its right. Fine. So I actually make a new node and I insert this particular node in here. And now I have to do the insertion for 11. So 11 is actually less than 12, so we move to the left subtree. So after we come over here, so now over here 11 is actually greater than 9, so we move to its right subtree. Fine. So now coming over here, because we found empty space, so we inserted 11 over here. So now I have to do the insertion for 2. How do I do the insertion for 2? 2 is actually less than 12, so we go to the left, and 2 is actually less than 9 also, so we go to the left. Now there is no more node over here, so I'll do the insertion of 2 over here. So basically insertion in BST is actually very easy and straightforward. But deletion in BST can get a bit tricky, but we will actually discuss them cases by cases, which will make the deletion also look very easy. Fine. So it is not a very a very hard thing to get, so we'll actually discuss that. So let's say we are having a BST, binary search tree, and we have to do the insertions in there. So let me just go ahead and make one binary search tree so that we can do the different deletions in there. 215, 13, 14, 20, 19, and this would be 21. Fine. And this can be 9. Fine. Okay, fine. So now there can be actually 3 cases. So whenever we are deleting any node in binary search tree, we have whichever node has to be deleted, it will actually lie in one of these 3 cases. So what are all these cases? So case number 1 is that the node which is to be deleted is a leaf node. So let's take this particular example that I have to delete this particular node. Then how do I delete this particular node? Because this particular node is actually a leaf node. So what I can do is, so whenever the node to be deleted is a leaf node, so I don't do anything, I just make its parent pointer point to null, and I delete this particular node, or I free this particular space. So there is nothing special that I do when I have to do the deletion of a leaf node. So I'll simply delete that particular node, and whatever its parent was pointing to, I'll make that pointer point to null. Fine. So this is actually a very easy example, and I mean a very easy case, and this particular case is also very easy, but the main case is this one only. So before moving to case 3rd, I'll discuss case 2 also. So let's say that the node which was to be deleted was having only 1 children. So let me take the case of this particular node 13. Now I am saying that this particular node has to be deleted. Then how will I delete that? I cannot really straight away clear this particular node. Why? Because this particular node can be deleted, but I have to take care of its children, because even after this particular node is deleted, something has to be done for its children, right? Because the children should still be accessible. The children should still be accessible even after I delete this particular node. Fine. So what I'll do is that whenever I was deleting the leaf node, I was making its parent pointer point to null. But whenever I am deleting a node with only 1 child, I'll make its parent pointer point to the child. So this particular pointer is removed now, and its parent pointer will now point to its child. And now because we have taken care of its only child, 13's only child, so now we can just go ahead and delete this node. So there is one extra step that we need to take care of, or that we need to do before we do the deletion of the node, and that is whatever my parent was pointing to, now it will point to its only children. The node which was to be deleted, so 13 was to be deleted and its only child was 14. So 13's parent pointer will now point to 13's child node. Fine. So 13's parent pointer is now pointing to 13's child node. So in this way we have actually we were able to take care of 13's only children. But what happens when when the node to be deleted is having 2 children? So this particular case is actually important. So I'll just rub it or clear the screen so as to make some space, and now I'll discuss this particular point also. So let me just go ahead and make one more, like 3, 10, 11, 9, 8. Fine. So, and this is 18, 17, let's say 14, and then over here I can have 15, over here I can have 19. Fine. So this is how my my tree is looking. Now let's say if I have to delete 10, let's say if I have to delete 10, because we are now discussing the case where my node is having 2 children. So how will I delete 10? So how do I delete 10? So in order to delete 10, or in order to delete any node which is having 2 children, there is only one step that I need to take. I need to replace this particular node's data with its in order successor or in order predecessor. So replace node's data, the node which has to be deleted, its data has to be replaced with its in order successor or its in order predecessor. Fine. So now the big question comes is that what is in order successor and what is in order predecessor. So fine. So what is in order successor? The element or the node which will be traversed or which will be processed right after this node. So what is that node going to be? In order successor is that, let's say if I am doing the in order traversal, let's say if I am doing the in order traversal for this particular tree, then if I process 10, now if I process 10, then what is the next node we are going to process? That would be tens. So tens, node 10 in order successor is actually 11. Why? Because if I will be doing the in order traversal of this, then it would be the element which is just greater than 10, which is 11 in this particular case. And what is the in order predecessor of 10? It is actually the element which is processed just before 10. Fine. So and what is in order predecessor of 10? So in order predecessor of 10 is actually 9. Fine. And in order successor of 10 is 11, because if you will do the in order traversal of this, you will find out that the in order successor of 10 is 11 and the in order predecessor of 10 is 9. But there is actually one more way to find out the in order successor and in order predecessor. So one way is that you do the in order traversal of the whole tree and you will eventually come to know that 11 will come after 10. Or what you can do is that you can do the in order traversal of the whole tree and you will eventually come to know that 9 is processed first and then 10 is processed right after 9. But that is actually a very lengthy task, right? So how do we find out the in order successor? It is the leftmost node in right subtree. It is the leftmost node in right subtree. So you actually take a note of this, that it is the left. What is in order successor of a node? It is the leftmost node in the right subtree. So if I have to find out the in order successor of 10, so it would be the leftmost node in the right subtree. In the right subtree there is right now in this particular case there is only one node only, right? So there is no left child. So this will become the in order successor. But let's say if my tree would have been this. So if I was to find out the in order successor of 12, then what would be the in order successor of 12? Go to the right subtree, and you find out the leftmost child. So leftmost child would be 14, right? So the in order successor of 12 becomes 14. Now if I have to find, so this is how we find out the in order successor of any node. Fine. And then the question comes that what is in order predecessor? What is in order predecessor? So in order predecessor is rightmost child in left subtree. In order predecessor is rightmost child in left subtree. Fine. So if I have to find out the in order predecessor of 9, then the left subtree, or if I have to find out the in order predecessor of 10, then what is the left subtree? This particular thing is the left subtree. Now I have to go to the rightmost child, but there is no rightmost child, so this particular node becomes the in order predecessor of 10. Fine. So in this particular case, this is how we were able to find out the in order predecessor of 10. But if I was to ask this, that what would be the in order predecessor of 12? What would be the in order predecessor of 12? So what will I do? I will go to its left subtree and I would try to find out its rightmost node. There is only 11 which is serving as its rightmost node. So the in order predecessor of 12 becomes 11. Fine. So this is how we find out the in order successor and the in order predecessor. Now coming back to this thing. So we were eventually discussing this thing, right? That the need this case third. So I'm removing this. So you take a note of this, that what is in order predecessor, rightmost child in left subtree, and what is in order successor. Fine. So now I'll just discuss that. Okay, so I was at this particular point, that in case the node to be deleted is having I just hope that the video is good. Okay, so so now coming over to this thing, that if the node to be deleted is actually having 2 children, then what will I do? Then I will actually do this thing, that I will replace that particular node's data with either its in order successor or its in order predecessor. So either I can replace 10 Okay, so I just hope that there is no buffering now. Okay, fine. So if it is clear, then we can just go ahead. Okay, so I was discussing this thing, that now we can now what we need to do is that we can replace the node to be deleted, which is 10, we can replace its data with either its in order successor or its in order predecessor. So when we do that, so I'll just go ahead and do that. So when we do that now, so let me replace 10 with 11, which is the in order successor. So now I'll write 11 over here and I'll write 10 over here. So now if once I do this particular step, my case third will either be reduced to case 1 or it will be reduced to case 2. That now 10 is to be deleted, right? But now either 10 will have only one child or 10 will have, in particular case, my case third is actually reduced to case 1. So now I can just go ahead and simply delete this. So this is how my deletion. Is it fine now? I'm not really, I don't really know. Is it like still buffering? Because my network speed is fine. I don't know if it's still buffering, but my network speed is fine. Let's check this. Why is this happening? Is this still okay, fine. I was like just checking this thing that it's like there is some continuous disturbance. Now as such, if it is clear, then fine. Okay, fine. So we were like on this particular thing now, that what we can do is that we can reduce this particular case third to either case 2 or case 1. And how do we do that? By performing this particular step, that is to replace nodes data with either its in order successor or its in order predecessor. Again buffering. Okay, Nidhi, I'll just repeat, but let me like try to get this thing right. I'll just try probably my mobile hot. Okay. Is it better now? Everything else is opening. Okay, fine. So I just hope that now it will work. Now it will work for sure. I just hope for the same. Okay, fine. So I'll just continue from where we left off. Again buffering. So clear कहते ही buffering होने लगता है. अच्छा, अब I just hope कि it's all clear now. Fingers crossed. नहीं, अभी तो चलो. Now it's clear. Fine. Okay, so I was like, I'll just rediscuss this particular case. This particular case third. So this particular case was that that when my node is having 2 children. So in case my node is having 2 children, then I will either replace it with its in order successor or that particular node's data with its in order successor, or I'll replace that particular node's data with its in order predecessor. Now if I do this particular step, then what will happen? If I'll actually perform this particular step, then my case third will actually be reduced to case 2 or it will be reduced to case 1. How? We will actually see. So let's take this example that I want to delete 18, that I want to delete this particular node. So let's say if I have to delete 18, then I will just go ahead and find out, let's say I'll replace it with its in order predecessor. Now how do I find out its in order predecessor? Its in order predecessor is the rightmost node in its left subtree. So there is no right node in its left subtree, right? So the rightmost node of its left child. There is no rightmost node of its left child, right? So 17 is the only rightmost node of its left child. So this is the 17 is the in order predecessor of 18. So what will I do? I'll just replace the data. So I'll just replace the data of 18 with its in order predecessor. So here comes 18 and here I am having 17. So now as you must have got reconnected now. Now it should work. It should work now. Okay, is it working now? I just hope that everyone is with me. Hello, is it like am I audible or am I reachable to you guys? Okay. हाँ, आप clear नहीं बोलेंगे. I was trying to do the deletion of 18 node. So did you like follow along when I did this particular deletion of the node of 18? If not, I'll actually repeat this thing all over again. Buffering? When is it buffering? I don't know. Okay, so like did you guys follow along when I was trying to delete this particular node 18? I just deleted this node 18. So did you like follow along till that particular point? In case you did not, I'll actually repeat that thing over again. I'm actually waiting for this particular answer. That did you like guys get this? If not, okay, so Supreet was saying no, so I'll just like quickly go ahead and just reiterate this thing because there was some issue. So I'll just reiterate this thing in a very quick manner. Fine. So because this is actually a concept which is important to understand. So this was how my tree looked like. Fine. So now I just wanted to delete 18. So whenever I want to delete 18, so I just went to that particular node and I just found out that the node which was to be deleted was having 2 children. Now because it is having 2 children, so now what I'll have to do is I'll have to perform this particular step. Now what will this particular step do? This particular step will actually reduce or convert the case 3 to either case 2 or it will convert it to case 1. So now what is this particular step saying is that replace node's data with either its in order successor or its in order predecessor. So now I'll just go ahead and find out 18's in order predecessor. So now what is in order predecessor? The rightmost child of the left child. So I just go to the left subtree and I try to find out its rightmost child. So there is no rightmost child, so this becomes my in order predecessor. So now what I have to do is that I have to replace the node's data with its in order predecessor. So that is exactly what I am going to do over here. So I'll bring 17 over here and I'll bring 18 over here. So as you can see that after performing this particular step, I have converted my problem from case third to case 2, because now it is having only one child. 18 is now having only one child. Fine. So now I can now do the deletion according to my case 2, which was actually very easy thing to do. What I do in case 2 is that I make sure that my parent's pointer now points to its, that 18's parent pointer now points to 18's child. So now 18's pointer will now point to 14, 18's parent, which was 17, its pointer will point to 18's child, which is 14. So now I can just go ahead and simply delete 18. So I'm not doing anything, I'm just following the steps that I actually told you, that how do I delete a node when it is having only one child. So after doing this particular deletion, this is how my tree will look like. Fine. So the main thing, the major takeaway from this is this particular thing, that I can convert my case 3 to either case 2 or case 1 by performing this particular step. And once I have converted my case 3 to either case 2 or 1, I can easily do the deletion part. Fine. So now Payal was saying that why not replace it with 19. So Payal, you can actually replace it with 19 also. So I am saying this now, that you can replace the node's data with either its in order successor or its in order predecessor. So you could have replaced it either with 17, which was its in order predecessor, or you could have also replaced it with 19, which was its in order successor. But here I actually replaced it with only in order predecessor. So you could have done it either of the ways. Fine. So now we will actually just go ahead and take one. Probably I'll just take so now we are done with this deletion, I just hope. Fine. So now I'll just move to one more set of questions, and this particular set of questions is actually, many questions are actually based upon this particular concept, and this is actually very easy to do, and I'll help you as to how to solve these kind of problems. Fine. So this particular problem says that I'm having a binary search tree. I am not really sure about that how do my binary search tree looks like, but I'm having a binary search tree and I have to find out, or I'm searching for the node 43. Then what can be the probe sequence? Probe sequence means which all node can I come across while I'm searching my node 43. So let's say if I have a binary search tree, so I'll just try to explain the question in a bit more clear way. So let's say I had my binary search tree looking something like this. Fine. So now if I say that I have to search for, let's say 8 or let's say 12, then what all nodes can I come across this? What is a possible probe sequence? So what all nodes can I come across this? I'll come across 20, then I'll come across 10, and then I'll come, because so I'll come across 20 because it is my root node. Then I'll see that 12 is actually less than 20, so I'll go to its left and I'll come across 10. and now I'll see that 12 is actually greater than 10, so I'll come across 12 only. So that is exactly what they are saying, that while I'm searching for 43, then which probe sequence is actually possible. So there are actually many questions based upon this particular concept only. So I'll just help you guys to like tell you a trick as to how to solve these kind of questions. So there is one thing only that you just need to, there is one step only that you guys need to just follow, and that particular step is this thing only. Okay, so Pooja has probably answered right away. Okay, so I'll check all the options one by one. Fine. So I'm right now I'm trying to find out that whether this particular probe sequence is possible or not. So how do I do that? I compare the node which I have to search, which is 43, with my node 61. Now because 43 is actually less than 61, so all the nodes after 61 should be less than 61. Why? Because once I have come across 61 and my 43 is lying in its, because 43 is less than 61, right? So it will be lying in its left subtree only. So that is why all the nodes after 61 should be less than 43, which is actually the case. So my test is actually passed for this particular node. So I'll do all this particular test on all the nodes. So now because 43 is actually less than 52, so all the nodes after this, so all these nodes should actually be less than 52, which is actually the case. So this is also, I mean, this particular test is passed on this particular probe sequence also. So now I come across this particular node. So now because 43 is greater than 14, right? So all the nodes after 14 should be greater than 14. So all the, because now whenever I came across 14, I actually compared the node which I had to search, which was 43. Now because 43 is greater than 14, so it will be lying somewhere in its right, since now should be greater than 14, right? So that is exactly what is happening. So this is the same thing that I'll do, that so now you compare 43 with 17. Now because 43 is actually greater than 17, so so all the nodes after 17 should be greater than 17, which is actually the case. So now you compare 43 with 40. It is still again and again buffering, yaar. Okay, so now, okay, fine, it's fine now. Okay, so I was onto this particular thing. So now I'll compare 43 with 40. Now because 43 is actually greater than 40, so it will look only in its right subtree, and so that is why all the nodes after 40 should be greater than 43. So all this particular test was getting valid on all these nodes. So I can say that this particular probe sequence is possible. So now let's just move over to the next probe sequence, which is 2, 3, 50, 40, 60 and 43, which was the last one. So now what will I do? I'll compare 43 with 2, and now I know because 43 is greater than 2, so all these elements should be greater than 2, which is actually the case. तो यहाँ पर तो condition valid हो गई. Now I need to compare 43 with 3. Now because 3 is greater than, 43 is greater than 3. So all these nodes should be greater than 3, which is actually the case. तो ये वाले पे भी condition valid हो गई. Now I need to actually check or compare 43 with 50. Now 43 is actually less than 50. So all these nodes should actually be less than 50, but this node is not less than 50, right? This is actually greater than 60. So this particular probe sequence is not possible. Why? Because when I came across 50 now, I compared 43 with 50. Now I came to know that 43 will lie somewhere in its left subtree, and all the nodes in its left subtree would be less than 50. But then how did we like come across 60? It is actually not possible, right? So that is why this particular probe sequence is not possible. So now I'll just summarize that what are the steps that you need to take. Fine. So this was the procedure, so I'll write all of them down in the form of a procedure. Okay. So now the procedure is this, that compare each node, let's term it as n, with node to be searched, which was 43 in this case. So for every node n, you compare the node n with the node to be searched. Let's say that the node to be searched was s. Now if n, so there can be two cases. If n is greater than s, then if n is the node which is we are coming across in this sequence is greater than the node to be searched, fine, then all the nodes after n in the probe sequence should be less than n. So this was my case 1, and here I am writing my case 2. Now if my node n, which was this in this particular sequence, if my node n was actually less than the node to be searched, then what you do? Then check that all the nodes after n in the probe sequence should be greater than n. Fine. So if you are just applying these two checks ना, इन दो चेक्स की वजह से ही आपको पूरा आंसर मिल जाएगा. अगर ये दोनों चेक्स वैलिड हो रहे होंगे मतलब तो वो वैलिड सीक्वेंस है, अगर नहीं हो रहे होंगे, कहीं पर भी एक भी एनॉमली निकली तो आप कह देंगे कि वो वैलिड प्रॉप सीक्वेंस नहीं है. Only B and E not possible. Okay, I didn't check with E, so probably now we can just go ahead and probably just take one more probe sequence. Fine. So I'll just erase this thing, and here we will actually take E probe sequence because someone is saying that E is also not valid. So I'll just check this, that whether E is also not valid or is it a valid probe sequence. So I'll compare 17 with 43. Now 43 is actually greater than 17, so this particular case. So then all the nodes after 17 should be greater than 17. So this is greater than 17, this is greater than 17, this is greater than 17, this is. So all of them were greater than 17. तो यहाँ पर तो ये valid हो गया. Now I come across 77. So now 77 is actually greater than 43. So this is the case. So then all the nodes after n should be less than n. सो ये 77 से कम है, ये भी 77 से कम है, दिस इज़ ऑल्सो लेस देन 77, दिस इज़ ऑल्सो लेस देन 77. So this particular condition was valid or got valid on this also. Now coming across, so whenever we came across this particular node, now we check this, that whether 43 is greater than or less than 27, because 43 is greater than, oh sorry, yes, because 43 is greater than 27, 43 is greater than 27, then all the nodes after n should be greater than n. So ये 27 से ज़्यादा होनी चाहिए थी, ये भी 27 से ज़्यादा होनी चाहिए थी, बट ये 27 से ज़्यादा नहीं है, तो इस केस में ये वैलिड प्रॉप सीक्वेंस नहीं हुई. तो ये वाली नोड के बाद मतलब ये कंडीशन जो है वो फेल हो गई, तो दैट इज़ वाई इट इज़ एक्चुअली नॉट अ वैलिड सीक्वेंस. फाइन. So these are the only two cases that you need to just check. So this is actually a very easy, problem set to solve. So you actually make sure that you don't miss out on this kind of questions. Fine. So this questions are very easy. Okay, so I'll just discuss them before I move over to heaps. So this particular thing is saying that I'm having a BST. Now what is the max? Having a BST with number of nodes is equals to 15. The number of nodes equal to 15. Now what is the minimum and the maximum possible height of T? Now what is the minimum and the maximum possible heights of T? तो वो कह रहे हैं कि so they are actually saying that we were actually having one BST and it is having 15 number of nodes. तो अगर मुझे 15 नोड्स दी हो तो मैं सबसे ज़्यादा बड़ा BST कैसे बना सकता हूँ? मैं वैसे बना सकता हूँ कि अगर मैं एक स्क्यू ट्री ले लूँ. सो लेट्स से इफ आई एम हैविंग 1 2 3 4 ऐसे करते 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 मैं 15 तक चले जाऊँ, तो ये मेरी मैक्सिमम हाइट हो गई ना. सो दिस वाज प्रॉबेबली ये आपको लग रहा हो ये मतलब ये हाइट 14 हो गई ना, क्योंकि ऐसे करते कि ये हाइट 0 मानी जाती है, देन ये हाइट 1, तो ऐसे करते करते इसकी हाइट हो गई, मतलब पूरे ट्री की हाइट हो गई 14, राइट. तो मैक्सिमम हाइट कैसे आएगी अगर मेरे पास एक स्क्यू ट्री है, और मिनिमम हाइट कैसे आएंगी अगर मेरा जो BST है. नाउ इफ आई हैव टू नो दैट हाउ विल माई मिनिमम हाइट कम, इफ माई so the minimum height is possible if my this particular BST is fully or completely is a complete tree. Fine. So if this is the case, or it is fully balanced, if I have to like term it, like this. Fine. So now what is the number of nodes in this? 1 2 3 4 5 6 7 8, I mean there are in total 15 only. Fine. So now what is the height of this particular tree? The height of this particular tree is 3. So now we actually like in this particular case we actually draw the tree, but in question I mean in paper if they would have asked you that if I am having 17, let's say 17 number of nodes, then what is the maximum height to possible would be 16, right? But what would be the minimum height possible? Because a complete binary tree में आपको पता है कि 2 raised power h और 2 raised power h plus 1 minus 1 के बीच में होती है nodes. This is something that we already have discussed. Let's say if I am having a complete binary tree, then the minimum number of nodes in that would be 2 raised power h and the maximum number of nodes in that would be 2 raised power h plus 1 minus 1. तो अगर मैं यहाँ पर क्या करूँगा कि अब मैं h की वैल्यू पुट करके देखूँगा, तो h की वैल्यू अगर मैं 3 पुट करूँ तो इट वुड बी 2 raised power 3 to 2 raised power 3 plus 1, 4 minus 1. So it would be 8 to 15. तो अगर मेरी 8 to 15 लाई कर रही होती तो मेरी हाइट 3 होती, बट यहाँ पर तो अभी मैंने मतलब एग्जाम्पल में लिया है कि 17 नोट्स है. सो इन केस आई एम हैविंग 17 नोट्स, देन of course my height would be 4. Why? Because if I'm having if I put 4, if I put h is equals to 4, then 2 raised power h will come out to be 16 and this will come out to be 2 raised power 5 minus 1, that means 31. तो अगर मेरी 16 से 31 के बीच में नंबर ऑफ नोड्स होती तो उस केस में मेरा मिनिमम हाइट जो पॉसिबल होती वो 4 हो जाती. फाइन. So this was actually like an easy example, but I still just wanted to discuss with you, although many of you have like answered on your own. Fine. So now I'll just quickly move over to what height balance trees are. Now what are height balance trees? Height balance trees have this particular, so what was the problem with BST first? Actually we discussed this, that the searching operation in BST, in worst case the time taken for searching in BST in worst case is actually order of n, right? Now if I have to improve this particular searching operation so that even in worst case it is able to perform the searching operation in order of log n, for that I need a height balance tree. Why? Because in my BST, if I am having a skew tree, then in that particular case my searching is considered as a costlier operation because it is taking order of n. But if I am having a height balance tree, then I will actually never be able to construct a. Okay, is it fine now? Okay, fine. So I just hope that it is not buffering now. Okay, fine. So fine, it is fine now. Okay. Okay, so I was on to this particular thing, that each and every node will follow this particular property. So now coming over to this particular tree, if I have to find out that whether it is this, so every node is basically balanced. Every node is actually a balanced node. So how do I find out this? So what will I do? That I'll try to find out the height of the left subtree. Now what is the height of the left subtree for this particular node? It is 1, 2. So 2 minus 1, which is 1 only, right? So this particular node is balanced. So now I'll check for this particular node. For this particular node also it is balanced because it is 1 minus 0 mod, which is actually less than or equal to 1 only. So for this particular node it is 0, for this particular node it is 0. So because all the nodes are balanced, so that is why we call that this particular tree is also an AVL tree. So basically the thing is that a height balance tree, or basically an AVL tree, is a binary search tree such that every node is a balanced node, is a height balanced node. Now what do I mean by a height balanced node? It means that the mod of the height of left subtree minus the height of right subtree is actually less than or equal to 1. Fine. So every node in AVL should follow this property. Now what is the searching operation in worst case time complexity? So now if I'll have an AVL tree which is actually a height balance tree, then in that particular case my searching operation can be performed in a much better way, and even in the worst case it will take order of log n time only. Fine. whereas searching in BST in worst case takes order of n. For BST I am saying. For BST it will take order of n, the searching operation in worst case. But in my height balance tree, the searching operation even in worst case will take order of log n. Fine. So you have got these three things, or I mean two things. So now these two properties were very easy, and I was like expecting that you many of you would be knowing this. So the main property is this particular property. So this particular property is very important, and you should take a note of this. So now let's say that I am having an AVL tree of height h. And I am having an AVL tree of height h. Fine. And I have to find out that how many or maximum number of nodes that are possible in an AVL tree of height h. Then how will I construct tree? I will construct a full binary tree, because a full binary tree is going to have the maximum number of nodes. Fine. So if someone says me that construct an AVL tree of height, let's say 3, such that it is having maximum number of nodes, then this is the way that I will actually draw my AVL tree in this particular form, which is that I'll draw it as a full binary tree, so that I'm having maximum number of nodes in my AVL tree. So this particular thing was easy, but how will you construct an AVL tree of height h such that it is having minimum number of nodes? That is actually the major thing to know about or to learn about. So now I have to construct an AVL tree of let's say height 1, then with minimum number of nodes. So I am first of all drawing this particular case, that I am drawing an AVL tree of height 1 with minimum number of nodes. Then this is how my AVL tree will look like. Now if someone says that draw an AVL tree of height 2 with minimum number of nodes, then if I draw just this now, this will actually not work, because this particular node is not balanced. So I need to balance this by drawing this particular node. Fine. So this is how my AVL tree of height 2 with minimum number of nodes will look like. So now I will actually, so you can although like construct an AVL tree of height 3 also just in manual way, but this will actually not work for bigger heights. So you cannot really do this in paper. So what I'll do is that I will actually give you an formula that you need to follow. So that formula is, so you'll be able to like understand that minimum number of nodes in an AVL tree of height h is actually equal to, so this is not a formula, this is actually a recurrence relation that I'm giving you. So the minimum number of, so nh is equals to minimum number of nodes in an AVL tree of height h. So this is what nh is denoting. So now if I have to find out the number of minimum number of nodes in an AVL tree of height h, then it would be, आप क्या कर सकते हो कि आप लेफ्ट सब ट्री के अंदर हाइट लेट्स से आप h-1, आप लेफ्ट सब ट्री को h-1 हाइट का बना दीजिए और आप राइट सब ट्री को h-2 हाइट का बना दीजिए. फाइन. तो इससे क्या होगा कि मेरी प्रॉपर्टी जो है AVL की वो फॉलो होती रहेगी. वो प्रॉपर्टी क्या थी कि द हाइट ऑफ द लेफ्ट सब ट्री माइनस द हाइट ऑफ द राइट सब ट्री इज लेस देन और इक्वल टू 1. सो दैट प्रॉपर्टी will be able to abide by that if we give or make my left subtree with height h-1, and if we make our right subtree with height h-2. So what will I write? So in this particular formula I am writing that the minimum number of nodes in an AVL tree of height h is equals to the minimum number of nodes in an AVL tree of height h-1, that will actually form my left subtree, plus the minimum number of nodes in my AVL tree of height h-2, that will form my right subtree, plus 1. Why plus 1? This plus 1 is actually serving or taking this particular root node or counting this particular root node. Fine. So I have like given you this formula, but how to use this? So I'll just give you this. So now in exam, if they ask you that tell me what is the minimum number of nodes in an AVL tree of height 1, then that would be, we know already that it is 1 only. We actually draw this now. And what is the minimum number of nodes in an AVL tree of height 2? Okay, sorry. The minimum number of nodes in an AVL tree of height 0 is actually 1. So this is an AVL tree of height 0 and it is having only one node. And this is an AVL tree of height 1 and it is having only 2 nodes. So n of 0 is equals to 1 and n of 1 is equals to 2. So this becomes my base case. Now if someone asks me that what is the minimum number of nodes in an AVL tree of height 3, so what will I use? I'll use this particular formula, that n of 3 is equals to n of 2 plus n of 1 plus 1. So my n of 3 will come out to be n of 2, which is, what is my n of 2? N of 2, I don't really know as of now, but I know my n of 1. So my n of 1 is 2 and plus 1. So how will I find out n of 2? I can find out n of 2 by using the same recurrence relation. N of 2 would be n of 1 plus n of 0 plus 1. So n of 2 would be n of 1 is 2 plus n of 0 is 1 plus 1. So 2 plus 1 plus 1 is equivalent to 4. Fine. So I just put n of 2 over here in this particular formula. I am able to get n of 3, which is 7. So an AVL, so the minimum number of nodes in an AVL tree of height 3 is equal to 7. So if someone asks me that can you please draw it for me, I can do that also. But the basic thing or the major takeaway is this thing. So if you can remember this particular formula and these two base cases, then you can answer that what is the minimum number of nodes in an AVL tree of, let's say, 7 also you can answer, n of 6 also you can answer, n of 5 also you can answer. So basically, majorly, they will not go beyond n of 7 because you have to do some calculations also in order to find out the answer. So they will not majorly ask you beyond n of 7. So now if someone asks you that what is the maximum number of nodes in an AVL tree of height h, then that is 2 raised to power h plus 1 minus 1. So this is a direct formula. But if someone asks you that what is the minimum number of nodes in an AVL tree of height h, then you don't have any direct formula for that, but you have a recurrent relation for that, and this particular recurrent relation can be used to answer this particular, to find out the minimum number of nodes in an AVL tree. So fine, so you should like take a note of this, because they might ask you that, in the exam, some questions related to this. So now I'll first of all discuss other different things about height balance trees also. So how do we do the insertion and the deletion in AVL trees? So the insertion and deletion in AVL trees is actually similar to BST only, but along with that we have to perform node balancing. So insertion in height balance trees or AVL tree is same as the insertion in BST, but along with that you will also have to perform one more step, that is node balancing. So this particular node balancing is actually an important addition that you have to do. Now how do you perform node balancing? By using clockwise rotations and anti-clockwise rotation. Fine. Now what are clockwise rotation? And so this is the case for deletion also, that deletion in AVL tree is equals to the deletion in BST plus balancing the unbalanced node. Node balancing also you can say it, or in if you have to tell it to someone in a sentence form, then you will say that balancing an unbalanced node. Now in order to perform balancing of an unbalanced node, you actually need to know two different type of rotations. One rotation is clockwise rotation and the other rotation is anti-clockwise rotation. So we are actually now going to discuss these two kind of rotations. Fine, so I'll just erase this off and I'll start. Now what is clockwise rotation? So let's say if I'm having a node X and we are having a node W and it is having a node A, it is having B and C, and I'm performing a clockwise rotation on a particular node. So I'm performing clockwise rotation on X. So clockwise rotation is performed on it can be performed on any particular node. So let's say in this particular case we are performing clockwise rotation on X. So how will that happen? If I perform clockwise rotation on X, then what will happen is that my W will come up. So there are only two pointer changes that happen. So my W will actually come up and its right pointer will now be pointing to X. So one pointer changes, that this particular pointer changes and this particular pointer changes. So X left and W right changes. Fine. So W right will now point to X and X left will now store W's left, whatever was the W's left children. So now these are the only two pointer changes that happen and rest is the same. Fine. So these two pointer changes happen, that W's right changes So W right will now point to X, and X left pointer changes. What will X left pointer point to? It will point to W's right children. So whatever was stored in W's right children, X left is equals to W right. So these are the only two pointer changes happen in clockwise rotation. Fine. So you take a note of this. So now I'll discuss what all or which two pointer changes happen, or what all operation happens in anti-clockwise rotation. So now, so before I so this two pointer changes was not good enough to like say this in a very easy manner. So what I'll do is that I'll first of all take an example. So let's say if I'm having a tree, let me just take any random BST or any AVL tree. So it would be 9, 11, 12, 13, 14. So now if I perform clockwise rotation on 9, so I'm performing clockwise rotation on 9, then what will happen? That 11 will come up, and 11's right pointer. Okay, so I'll probably write this thing in a more clear way. So what will happen if I perform clockwise rotation on 9? These are the changes that will happen. So 11 will come up and 9 will become its right children, and whatever was the right children of 11, it will become 9's left children. Okay, so this was not a, so the example that I took was not that of an AVL tree. So I was basically like trying to just explain you this particular thing, the clockwise rotation. So in that particular process I forgot to take the right example, so I'll just like retake that particular example. Fine. So 7, 6, 8, 10. Fine. So now I'm performing clockwise rotation on 9. So when I perform clockwise rotation on 9, so I have to perform rotation in this particular direction. So 7 will come up and 9 will go down. So 7 will come up and 9 will go down. Fine. And 6 will remain in its place. But what will happen to this particular child? It will become the left child of 8. So as you can see that even after performing clockwise rotation, the BST property is still intact. The BST property was intact in here also, and after performing clockwise rotation also, it is intact here also. Why? Because all the left child are less than their root and all the right child are greater than their root. Fine. So this is how we perform clockwise rotation. So now I'll discuss about anti-clockwise rotation. So in case you guys want to take a note of this, you can take a note of this. So there are only two pointer changes that happen in clockwise rotation. So now I'll discuss about anti-clockwise. Okay. So now in anti-clockwise rotation, what happens is that you so let's say this was how it looked like: A, B, C, and you want to perform anti-clockwise rotation on X. Then there are two pointer changes happen. Now W will come up. So now W will come up and X will go down. Fine. So what was the one pointer that changed? W's left pointer changed. So W's left will now store X. And another pointer that changes is this one, that because now X left will store A. So X left will now store the left children of W. Fine. So these are the only two pointer changes. So the basic or the main thing is that whenever I am performing anti-clockwise rotation, my W goes up and my X comes down in my anti-clockwise rotation. So now if I have to perform, or if I have to take an example, then it would be this 9, 8, 10, or let's take it as 11, 10, 12, 7. So now if I perform anti-clockwise rotation on 9, so I can actually perform anti-clockwise rotation on any of the node, but I am right now performing anti-clockwise operation on 9. So now if I do that, so Khushbu is saying that but this tree is balanced. Khushbu, actually this tree is balanced, but I am just right now telling you the main concept of what is rotation, what is anti-clockwise rotation or what is clockwise rotation. I am not really answering you that how do you balance an unbalanced node. So we will actually see that how do we balance an unbalanced node also, but that will actually mainly need these two operations to be performed. So I'm right now I'm just discussing about these two operations. So now if I perform anti-clockwise rotation on 9, then what will happen? Then 9 will go down and 11 will come up. So 11 comes up, 9 goes down, and everything else will remain intact. And what is the only change that will happen? That 11's 10 will go or come in over here. So now as you can see that BST was valid over here as also, and BST is now valid over here also. Fine, right? So now this is how we perform anti-clockwise rotation. So now main thing happens, that how do you actually balance an unbalanced node. X के लेफ्ट में तो C है ही नहीं, ओके X के लेफ्ट में C है एक्चुअली साक्षी, तो इसलिए C यहाँ पर आ गया था, और जो W का लेफ्ट चाइल्ड था वो X का लेफ्ट बन गया, सॉरी X का राइट बन गया था, सॉरी जो X का लेफ्ट चाइल्ड था, W का जो लेफ्ट चाइल्ड था वो X का राइट बन गया. फाइन. सो मेन थिंग यही है कि अगर आप एंटी क्लॉकवाइज रोटेशन कर रहे हो तो 11 ऊपर आ जाएगा और 9 नीचे चला जाएगा. अब 11 ऊपर आ रहा है और 9 नीचे जा रहा है तो उसका लेफ़्ट पॉइंटर तो ऑफ कोर्स चेंज हुआ ना. अब ये इसको खाली तो नहीं छोड़ सकते, तो हम क्या करते हैं कि इसको राइट के साथ जोड़ देते हैं, मतलब 9 के राइट के साथ जोड़ देते हैं. फाइन. सो नाउ आफ्टर डिस्कसिंग clockwise and anti-clockwise rotation, I'll discuss about insertion. So now in insertion we were discussing this thing, that while we are doing insertion in AVL, we will do the insertion in the same way as we do in BST. So let's say I already had one let's say AVL tree which was looking something like this. ठीक है. So this is an AVL tree. Now let's say I wanted to insert 6. So I'll do it in the similar way. So what I'll do is that 6 क्योंकि 11 से कम है तो I come to the left. Now because 6 is less than 9 also, so I come to the left. Now 6 is less than 7, that is why I again come to the left and I do the insertion. Now the last thing is you check from the node that you have inserted, you start checking that whether all its parents or all its ancestors are balanced or not. So 6 is balanced, 7 is also balanced, 9 is also balanced, this is 11 is also balanced. So this was balanced. So now, but now let's say if I insert 5, so now 5 will come in over here. So now we perform the node checking that whether they are balanced or not. So 5 is balanced, 6 is balanced, but 7 is not balanced. Fine. So now because 7 is not balanced, so we will actually perform the node balancing on 7. So we will actually perform the node balancing on 7. So now in this case, why did this 7 become unbalanced? So this 7 became unbalanced because it is having unbalancing in its left and again left child. So basically now we will learn that how many types of unbalanced nodes can we come across. So in this particular case, this 7 node is actually an example of an LL unbalanced node or a left child unbalanced node. So in this case, in this similar way, there can actually be 4 types of unbalanced nodes: LL unbalanced node, RR unbalanced node, LR unbalanced node, or RL unbalanced node. Now how do I actually identify that what kind of unbalanced node it is? So that is also like very easy. So in this particular case, I was very easily able to see that where did the unbalancing come from. So I was able to see because of the insertion in left and left, this is from where my unbalancing came from. So in case of my LL, I simply do clockwise rotation. I simply perform clockwise rotation on 7. Okay, so just give me a second. Okay, so in LL, if my unbalanced node is of type LL, then we simply need to perform the clockwise rotation on 7. Fine. So I will perform clockwise rotation on this particular node. So when I perform clockwise rotation on this particular node, my 6 will come up and my 7 will go down. Fine. So now this is how I'm able to balance this particular node. Fine. So this is how my balancing happens in LL kind of a node. So now let's say after this, I have discussed this particular case and we have seen that how my LL unbalanced node looks like. But I don't really know, as of now, I don't really know that how do my RR unbalanced node looks like. So I'll just take an example of that and I'll show you that how do my RR unbalanced node or right unbalanced node looks like and what operation do we perform to balance our RR unbalanced node. Fine. So I'll just rub this off. So in order to like so let's say this was 6 and I did one insertion 7. So this was my tree. Now I one operation came in that I have to do the insert 8. So I went to the left, this is 9, again I went to the left because 8 is actually less than 9. So now coming over this particular node at 6, because 8 is actually more than 6, so I go to the right. So now after coming at this particular node, because 8 is actually greater than 7, so I come over here. Fine. So now this is how I have inserted my 8. But now I need to go across this path till I come across my root node, and I need to find out whether all these nodes are balanced or not. This particular node is balanced, this is balanced, but what about this particular node? The height of left subtree is 0 and the height of right subtree is 2. So this is not balanced and I need to balance this. But before I balance this, I need to find out that what kind of or what type of unbalanced node it is. So now as I can see that unbalancing came because of my insertion in right child. Fine. So that is why I was able to identify it as RR unbalanced node. And what do we do in RR unbalanced node? We simply perform anti-clockwise rotation on my unbalanced node. So we simply perform anti-clockwise rotation on my unbalanced node. So this was my unbalanced node, which was 6. So how do I perform an anti-clockwise rotation on this? My 7 will come up and my 6 will go down. So this way I was able to balance this particular node also, and all the nodes, once I have balanced this particular node now, then all the nodes till root will by itself be balanced only. So this is how I balance my RR unbalanced node. Fine. This is how I balance my RR unbalanced node. Fine. So now I was able to see that what do I need to do, or what all operations do I need to perform in case of LL unbalanced node, and what all operations do I need to perform in case of RR unbalanced node. So now I just need to check that what all operations that I need to perform on my LR unbalanced node. Fine. So I'll just take that. So in the exam you'll be able to identify that what kind of unbalanced node it is, but you just need to remember this thing only, that in LL I perform clockwise rotation on my unbalanced node, and in my RR I perform anti-clockwise rotation on my unbalanced node. And what do I do in LR? I'll just discuss. Fine. So before that I'll just take an example. So now this was how my tree looked like. So I'm actually right now going to discuss about RL first, then we can discuss about LR, but first of all we are discussing about RL. So let's say that now an operation came in, this is how my tree was, and an operation came in to insert 7. So once I come across this, so 7 was lying to the right of 6, so we come over here, and 7 should lie to the left of 8, so we come over here. So after doing the insertion of 7, I'll have to check over this path that which particular node, in case it has got unbalanced, which particular node has got unbalanced, and how do I balance that. Fine. So on that path, I start off from here. This particular thing is, node is balanced, this is also balanced, but coming across this particular node, so when I came at this particular node, I found out that the height of left subtree is 0 and the height of right subtree is 2. So that is why this is not a balanced what do you say, this is not a balanced, height balanced AVL tree. Okay. So we now need to find out that what kind of unbalancing is there in 6. So now because 6 is an unbalanced node, right? So now how do I find out? I just tend to see that because I was returning from this path and then I came across this. So ये वाला path आया कैसे था? राइट एंड देन लेफ्ट जाके. एक्चुअल में मैं ऐसे ही तो चेक करता हुआ जा रहा था सारे नोट्स को, बट ये वाले पाथ में मैं आया कैसे था? पहले मैं राइट गया था और फिर मैं लेफ़्ट गया था. सो इससे मुझे पता लग गया कि आर एल जो है ये आर एल टाइप अनबैलेंसिंग है. सो माई 6 नोड इज़ एक्चुअली आर एल अनबैलेंस नोड. सो आई हैव टू फर्स्ट कन्वर्ट माई आर एल अनबैलेंस नोड टू. So in case of my RL unbalanced node, first of all I perform I convert this RL to RR. So first of all my RL kind of unbalanced node is actually converted to RR. How is it converted to RR? By performing clockwise rotation on its right side. Fine. So I convert. So the step number 1 is convert RL to RR. क्योंकि हमें ये तो पता ही है कि RR को कैसे हमें सॉर्ट आउट करना है, by performing anti clockwise on the unbalanced node. बट मुझे RL का नहीं पता कि RL को कैसे करना है. तो अगर मैं RL को RR में कन्वर्ट कर दूँ तो मेरे लिए ईजी हो जाएगा. तो बट RL अनबैलेंस नोड को RR में कैसे कन्वर्ट करते हैं? बाय परफॉर्मिंग क्लॉकवाइज रोटेशन ऑन इट्स राइट साइड. तो मैं यहाँ पर अगर क्लॉकवाइज रोटेशन लगा दूँ तो मेरा कैसे हो जाएगा ये वाला ट्री? 7 ऊपर आ जाएगा और 8 नीचे आ जाएगा और ये सब ख़त्म हो जाएगा. फाइन. सो आई विल जस्ट क्लियर इट अप अ बिट मोर. तो मैंने सबसे पहले क्लॉकवाइज रोटेशन लगा दिया. सो कैसे आप कन्वर्ट करते हो RL टू RR को? बाय परफॉर्मिंग क्लॉकवाइज रोटेशन on right child of unbalanced node. On right child of unbalanced node. This is how you convert RL to RR. क्योंकि अब आपको दिख रहा है ना कि RL था, पहले RL था बट अब वो RR हो गया. अब तो आपको आता ही है कि आपको RR को कैसे बैलेंस करना है, बाय परफॉर्मिंग एंटी क्लॉकवाइज ऑन दिस पर्टिकुलर नोड. तो मेनली जो है यही स्टेप एक्स्ट्रा है एक RL के केस में. तो अब आप एंटी क्लॉकवाइज इस पे लगा दीजिए. 7 आपका ऊपर आ जाएगा और 6 नीचे चले जाएगा। तो 7 आपका ऊपर आ गया, 6 नीचे चला गया और 8 तो यहाँ पर था ही। तो अब इस ऐसे में ये करके मतलब आपने अनबैलेंस को बैलेंस कर दिया। तो मेनली बस यही था। आरआर का तो आपको पता ही है, तो मैं आरआर को मैंने रिपीट नहीं किया, बस मैंने ये बताया आपको कि आरएल से आरआर में कैसे आप कन्वर्ट करते हो बाय परफॉर्मिंग क्लॉकवाइज रोटेशन ऑन राइट चाइल्ड ऑफ अनबैलेंस नोड। इस तरीके से आप आरएल को आरआर में कन्वर्ट कर सकते हो। फाइन। सो सेम इज़ द केस फॉर एल आर ऑल्सो। तो एल आर के केस में आप पहले इसको एल एल में कन्वर्ट करते हो। कैसे? बाय परफॉर्मिंग एंटी क्लॉकवाइज rotation, by performing anti-clockwise rotation on left child of unbalanced node. By performing anti-clockwise rotation on left child of unbalanced node आप LR को LL में कन्वर्ट कर सकते हो। तो मैं इसका भी एक बार एग्जांपल दिखाता हूँ। तो ये आप नोट कर लीजिएगा, या तो आप वीडियो पॉज करके मतलब नोट कर लेना। सो यू प्लीज़ नोट दिस डाउन बाय जस्ट पॉजिंग डाउन द वीडियो सो दैट आई विल जस्ट मूव अहेड। So my 6 was over here. So now let's say this is how my AVL tree looked like. Now I did the insertion of 7. So one more command or one more operation came in that inserts 7. So I just inserted 7 over here. So I need to check along this particular path, right? So this is balanced, this is balanced, but this is not balanced. Fine. So how do I balance this? Because first of all I check that what kind of unbalancing is this. This is left right. So this is LR type of unbalancing. In case of LR type of unbalancing, I first convert it to LL type of unbalancing. How do I convert this? By performing anti-clockwise rotation on its left side. So I perform anti-clockwise rotation on 8. So 7 will come up and 8 will come down. So this will become something like this. So I'll just rub this. Six, 7, 8. ठीक है? Oh, okay, fine. So this is how it will look like. So now as you can see that it has been converted to LL unbalanced node now. So now you already know that how do you balance a LL kind of unbalanced node by performing the clockwise rotation on the unbalanced node. So you perform the clockwise rotation on this, your 7 will come up and your 6 will go down, and this is how your tree will look like now. So fine. So this was very easy. So I hope that I was able to like make it or simplify this, that how do you balance an unbalanced node if it is of type LL or RR or LR or RL. Fine. So I just hope that I was able to like make them easy. So in the next class, probably tomorrow, so actually there is one 2-hour class, right, in the morning for you tomorrow. So probably because I was to complete this heap part also, I mean I was supposed to complete it today only, but probably heap will still take another 1 hour. So I will tomorrow first of all discuss a few things, only a few questions about height balance trees on this particular thing only, balancing an unbalanced node. I will show you some more examples on this, probably 1 or 2, and then we will complete this heap in 1 hour class. Probably I'll take that 1 hour class in the morning, probably after your regular class is over. I'll take 1 hour class in the morning, and then we can like stick to our schedule of 9 to 11, so that and in tomorrow's 9 to 11 class we will complete stack, queue and linked list, the questions on stack, queue and linked list. And in this 1 hour class that I will take in the morning, I'll let you guys know that when will this class happen, but I will actually have to take this class just to cover heaps, because we have actually like lagged a bit. We probably like covered this whole thing, I mean trees thing, in a bit slow manner, so I'll cover this heap in 1 hour class tomorrow. Fine. So I'll meet you guys tomorrow, and thank you so much for joining in, and good night. Okay, bye bye. And in case of any doubt, you can always ping on the WhatsApp group, or you can write us on qa.acadflix.com. Fine. Okay, so the night class timing, I'm right away giving you that it would be from 9 to 11 p.m. only, but for this 1 hour class, I'm not really sure about this, because I don't really know the timing of other educators on Acadflix. So I'll probably consult them once, and by tomorrow morning only I'll let you guys know that when will this 1 hour class happen. Fine. So thank you so much, and I'll meet you guys tomorrow. Okay, bye bye.